You might also hear the term indirect variation instead of inverse variation. It's the same thing. Okay, we talked about directly related parameters yesterday. These are going to be indirectly related. Example, simple, right? The more you exercise, well, I'm not sure this is. I was saying, the more you exercise, the lower your weight is, but that's not always true, right? You can exercise all you want, you might not lose weight or anything, but let's say the more you study late at night, the less you sleep. Okay? Indirectly related. As one goes up, the other goes down. In science, as potential energy goes up for an object, kinetic energy usually goes down. There's a conservation there, a balance. Okay, so we're looking at things that vary indirectly. And now, today we're going to see things, you remember yesterday at the very end we talked about things that vary with multiple parameters. We'll see that today, but with directly and indirectly together. So the general function for this is y equals k over x. What was the function for direct variation?
Y equals k.
Yeah, y equals kx. So the only difference, obviously, is that x is in the denominator. And if you don't see that this is actually true, if you're not certain that this is true, all you got to do is check it out. Ready? So let's say we have, let's say we have an unknown number here, y, and let's call k 20. Right? If I let x equal 4, what do I get? Okay. If I increase x to now make it 10, what do I get instead? So as I increase x, y is decreasing. That's the whole idea behind indirect variation. As one thing goes up, the other goes down. Okay, and this curve is the general curve that shows indirect variation. As this value of x increases, the value of y decreases. It goes down further as I go along this track. You'll see that these points all line up. If I take a look at this, this is 1 and 1, so this is the point 1, 1. 1 times 1 is 1. This is the point 1 half, comma 2. 1 half times 2 is 1. This is the point 2, comma 1 half. Multiplication of those two would also give you 1. So what I'm getting at is this fact. And this is obvious because you could just rearrange this. How would you get k by itself? You would multiply both sides by x right here, bringing this x over here, becoming xy equals k. And that's another way of writing it. So either way you want to write it is fine. Now, I recommend writing it the first way on the left when studying the behavior of an actual function, because functions are written as y equals something else. If you're solving a problem where you have some x values and y values that are known already, you could use the right side. And I'll show you where we'll use that today. There's an example that we work on that is not tricky, but it's easier to use this method actually for one of them. And I'll point that out when we get to it. So let's jump. If C is inversely proportional to D, and C is 2 when D is 3.6, find C when D is 4.5. So go ahead and practice part A on your own. Use the generic function we wrote on the previous slide. This is kind of like a, relatively easy example of this. Use the function from the previous slide, or the idea of it, of inverse proportion, to write a relationship between C and D. And use K for your constant again. So before you do A and B, you should really start with this, right? And you could have actually used that other form and said, well, K equals XY. y times x, or CD in this case. We give us 7.2 for k. That's the first thing we want to do. Once you have that, you could write your general function. And the first part says find c when d is 4.5. All right, so that's all we really have to do for this one. 7.2 over 4.5. For part B, and you can come up with, what does that end up being? I don't even know. 1.6. For part B, it asks, determine the value of D when C is 6.4. Well, in this case, you could start with the generic function, or you could use that second way of writing it. Either way works. But if we're given C as 6.4, that would go in here. K is 7.2, and the unknown then would be D. To get D by itself, what should you do? To get D by itself. Simple way to move things with three variables there. Alex?
You multiply D both times.
Mm-hmm. And then?
You divide 6.4 to 7.2.
Very good. So just switch these two, okay? Put D up here, and put the 6.4 down here. 7.2 over 6.4, 1.125. Right? So the concept is almost the same as yesterday, except it's just the opposite that's happening. That's it. Okay, now, before I look at the next few examples with you guys, it's really important that you understand the difference between these two. Because when you study any type of science, everything is about direct and indirect variation. Everything you do. Sometimes they're squared, sometimes they're things that are cubed, or they're, x to the 1.7 power, fine. And that'll make it a little bit different, but the concept of being directly related versus indirectly related, it is everything you learn in anything that's like math-based science. Chemistry next year, physics the year afterward. Every formula you study in physics has direct and indirect variation. Some only have one, but it has some form of that. And understanding the physical nature of it makes the most sense. So to give you a simple example, all right? This is an example that you'll learn about in physics for direct and indirect variation. If you, magnetism, sure, let's do that. How many of you as kids played with magnets? Right, you know how magnets work? When do they stick together? When do they repel each other? How do they work? What are the basics? You remember or no? Well,
like positive and negative attract, and then positive push away from each other.
yeah, so likes repel, opposites attract. And you're giving electrical terms, but it's the same thing, north and south. So positives repel or negatives repel. But a positive and negative together would attract. And that's the electrical force between two objects. You could also look at the magnetic force. Two norths would repel. Two souths would repel. But a north and south pull together. Now, what I'm asking you is this. When you were a kid, you might not know right now, but when you took magnets, as they got closer together, what happened? Imagine, that the poles were like one was north and one was south. When you brought them together, what happened eventually? Yeah. Suddenly they would just snap together, right? For a while, they would not feel any force, and you might feel a little tug, right? You might feel like there's a little bit of a tug, like a pull that way. But once they get close enough, they snap together. They pull each other together. Here's the reason. The formula that governs electrical force and magnetic force has to do with the distance between them. But the formula here, the force, is indirectly related to the square of the distance between them. So what does that mean? If I decrease the distance, I'm decreasing the distance by bringing them closer, right? Since they're indirectly related, if I decrease the distance, what's happening to the force?
It's stronger.
It's getting stronger. That's why they snap together at the end there. And especially because of the fact that it's squared. So if you decrease the distance by a factor of 5, you're increasing the force by a factor of 25. Okay? Again, let me prove that to you in case it doesn't make sense. So I have some distance between these two particles, and suddenly I take that distance and I quintuple it. I increase it by a factor of 5. Well, in essence, what does that do? It makes that value in the denominator that I'm seeing there really k over 25r squared, right? Your laws of exponents, we know that when you raise a product to a power, that power gets raised to both of those factors within the product. So this becomes 25r squared. Okay, this value becomes 25r squared. So if I'm increasing the distance between them, I'd be decreasing the force. In the example I gave a moment ago, what did we do? We didn't increase the distance, we decreased it. So we did something like this. Oops, not K, but R. Like that, that's what we were just talking about. We took the distance and cut it in fifths, or into a fifth. So as a result, this would become K over 1/25 R squared. What happens when you divide by fraction, really? When you divide by fraction, what are you really doing?
You're multiplying by the denominator of the fraction, or the reciprocal of the fraction.
Exactly, you're multiplying by the reciprocal. So this would in turn really be just K over R squared times 25 over 1. So as a result, the force increases by a factor of 25 when the distance gets cut into fifths. So those are indirectly related. But I want you guys to see that this is just one of the many, many examples. Gravity, same thing. The gravitational force is G m1 m2 over R squared. It's directly related to the mass of the objects, and that makes sense. The Earth has a lot of mass, thus there's a gravitational field. How many of you have seen Family Guy before? A few of you? Okay. There's an episode with Peter, and Peter starts to gain a lot of weight in the episode. Peter's the main character on the show. It's like an animated series. And Peter starts gaining weight in the episode, and Brian the dog is like, Peter, you're getting so heavy, it's getting out of control. And he's like, oh, whatever, Brian. And then like 5 minutes later in the episode, Brian goes, Peter, you've gotten so heavy that you've developed your own gravitational field. And then the dog, Brian, who talks, starts throwing stuff at Peter, like a TV throws at him, throws a bunch of stuff at him, and you see those things start to orbit around Peter. It's because the mass of the object is what really generates the gravitational field. So the Earth is this sphere of mass that's warping space around it, causing gravity to be stronger, or gravity to have an effect because of its mass. This stylus and this water bottle, they have mass. So there is a gravitational force between them. There's literally something pulling these together. But it's so insignificant because the masses are so small. So if you think about the gravitational formula, and I might actually pull it up in this section, do I? I do, yeah. I actually talk about it at one point. So if you look at the gravitational formula, we'll see, and I'll skip the slide when we get to it, but this is what I was talking about. We'll see this. We'll see that the force of gravity is directly related to the mass of the objects because it's in the numerator there. But if we look at the distance between the objects, that's in the denominator. So these are indirectly related, whereas these are directly related. Okay? Anything that appears in the numerator of a formula, you could jot this down, it will help you a lot in any science class. Anything that appears in the numerator of a formula is directly related to the variable you're solving for. Anything that appears in the denominator is indirectly related. And that's where y equals kx and y equals k over x really comes from. Okay, again, side note if you want to write it down, but you have this already written in your notes. These are the two formulas we've been studying. The first one is direct variation on the top. The second one is indirect variation. With direct variation, this x is really in the numerator here. This x up top is really in the numerator. Well, this x in the bottom here is in the denominator. Okay, so this is direct variation, showing that anything in the numerator is directly varying. But anything in the denominator, this is indirect variation, is indirectly related to the, you can call this the variable of interest, the variable you're solving for. Okay? Alright, let's, try this one on your own, see what you get. And be careful, please. Okay, there's one difference between this one and the last problem you have to recognize right away. Starting point, what do you got?
I did the formula for, I got H equals K over R squared.
Take a look up, see if you got that. Okay, that should be your starting point for sure. It says that the height is inversely proportional to the square of the radius of the base. Not the square root, be careful, because some people make mistakes in this and put a radical around the R. Okay, it says the square. Continue, Morgan.
I plugged in 15 times, so 15 equals K over 10 squared. Then 1500 is K.
Okay, and from that information, what can I then write?
Like 60 equals 1500 over R squared.
Yeah. Okay, 1500 over R squared, and as Morgan was saying, we're plugging in 60 for the height. It says, find the radius of a second cone of equal volume with a height of 60 centimeters. Believe it or not, as easy as this looks, this would be like a medium to difficult level question on an SAT. You should be able to do this like that. Okay, these problems are not that tough, so you should definitely be able to. James? Yep.
I got 5.
What'd you get? 5? Agreed? Yes? Okay, what did James do? He moved R squared up. He moved the 60 down below. 1500 over 60 is really 150 over 6, which is 25. But since 25 is R squared, he said R must be 5. Now obviously it's plus or minus, but why didn't James include the negative here? Why didn't James say plus or minus 5? Why doesn't the negative matter? Jeff?
You can't have a negative number.
Yeah, we're looking at dimensions of a figure, right? So you can't have negative 5 as your radius, so it's just going to simply be 5. Okay, good job. The next slide is just demonstrating what I was talking about. Okay, direct and inverse variation at the same time is what we've been saying. So this is specifically what I'm talking about earlier. And we have the gravitational law, Newton's gravitational law tells us that the attraction between any two bodies is directly proportional to their masses and inversely proportional to the square of the distance between their centers. So it's directly related to their masses, so I start with this. Okay, direct variation right there. It's directly related to both masses. But it's inversely proportional or indirectly related to the square of the distance between them. So put that over R squared. Again, directly related to the masses, indirectly related to the square of the distance between those two bodies. Let's see an example with electricity and electric fields in the next one. Spend a minute just looking at this to write out the actual statement, please. God bless you. Just to write out the actual statement. Notice no variables are given, right? There's no letters or anything, so you have to come up with your own or use your own in this case. What do you have for this? It says the electric field. What would you use for electric field? What letter? Will? Yeah, probably E for electric field. And that's what is used actually. The electric field produced by a charged particle varies directly with the charge on the particle. Varies directly. So what do I write next? And what am I going to use for charge? Doesn't matter, honestly. That works. Now, actually, let's not use C only because the units here are given in coulombs, not to confuse it. It doesn't pick any other variable. Okay. Okay, the electric field produced varies directly with the charge. So we have electric field varies directly with the charge, F. Now, as a result, we also know that it varies inversely as the square of the distance from the charge. So what is that going to look like again? Inversely with the square of the distance from the actual charge. Jeff?
Put half, multiply half by t squared.
Good. By some variable squared. Very good. Okay, so E is electric field, F is charge in this case, D is distance from the actual charge. On a planet galaxies away, the electric field felt at a distance of 13 meters, so 13, right in the denominator. From a charge of 25, that goes in for F. Oh, sorry, from a charge is, not from 25. Let me go back and emphasize this, because I think last year this was a problem that brought up. On a planet, the electric field is at a distance of 13 meters. So that's definitely D. The electric field felt at a distance of 13 meters from a charge. The electric field itself is 25 newtons per coulomb. So that 25 is going to go in for the actual electric field itself. And it's not easy to see that because you see a charge, it looks like this is saying a charge is, right? It looks like that's saying a charge is 25, so you'd have a desire to put the 25 in here for charge. But again, read it carefully. It says the electric field felt at a distance of 13 meters from a charge is, what is? The electric field felt is 25. So again, the electric field felt is 25. This piece in here is just saying that this is 13. When the charge on the particle is 8 coulombs, that's going to go in for the actual charge right here. So we've got 25 equals K times 8 over 13 squared. So just manipulate your formula a little bit to get K by itself. Move the 13 squared over, divide by 8. I think K is it an exact answer or is it a decimal? I put approximately on mine, so probably is it a decimal. What do you again, Chandler?
528 point, 1/8.
528 and 1/8. Nice. 1.125?
Yeah.
Very good. 528.125 or 528 and 1/8. Okay, that's the K value. Very good. Now, the rest of the problem says, after that, to determine the charge, so determine F, right, the charge, not the field, but the charge, which might have been a little bit counterintuitive with the F of the field, right? Determine the charge that would produce a field of 18 newtons per coulomb at a distance of 11 meters. So we're determining the charge. So we have our general formula we can write. Electric field equals K, times the charge over, you called it D earlier, right? Yeah. All over the distance from the source squared. So that's the original formula we're going to use, but we plugged in for K, obviously, because we determined K in the previous part. Now the rest of the problem says to determine the charge. When it says determine the charge, we are looking for this variable right here. Okay, that did not work out too well. Okay, we're looking for that variable F right there. That's what we're trying to find. It's really important to know what you are actually talking about. And what do I mean by that? I mean, like, you need to recognize what each variable is in your formula. How might you be able to remember what they are? What should you do when you start the problem?
Write it down on the side of each values.
Yeah, what are those called? When you define a variable, you make your...
Statement.
Yeah, exactly. Make some let statements. E is electric field strength. F is charge. D is distance from the source. So now, because this problem says determine the charge, you recognize right away that you're looking for F, which is represented by charge. You're told that the field is 18 newtons per coulomb. The distance is 11 meters from it. So I've got 18. And in the denominator, I've got an 11, and that's going to be squared times F. So all we need to do here is solve for the charge F. Okay, solve for the charge F. And that's what we'll end up getting, right? Which is around, I think exact, 4 1/8, 4.125, is that what it comes out to be? Is it exact?
I got 4.124, that's what I'm guessing.
Okay, so it probably is, and I rounded, that's why. Okay. So 4 and change, 4.12 we'll say. What would the units be on that? If you're doing a problem like this. What would the units be? And if you have trouble understanding, just go back to your problem and look at it. What would the units be for my answer? You don't have to give me a word, just give me the letter, the abbreviated letter.
C.
Yeah, capital C. Okay, if you look back at the problem earlier, charge was defined as, if I recall correctly, 8 coulombs. 8C. C is coulomb. It's a scientist's last name. 8 coulombs. So as a result, if you're looking for a charge, and earlier charge was defined in coulombs or as C's as the units, that would be the same unit here. It doesn't really matter. Okay, right now, doesn't matter. But when you get to physics, all this stuff plays a role. Okay, units are huge in physics. It would be coulombs. That would be the actual value for the unit. All right, try the last one on your own. This one is not tough, but okay, it's not really tough, but it's a little bit tricky. It's tricky because it's really, really wordy, this problem. It would definitely be a difficult level problem on the SAT. You can do this, I mean, in about, I don't know, give yourself a minute or two. If you could do this in about 2, maybe 3 minutes at max, that's pretty good speed for this. Because in the SAT, it takes about like a minute to 2 minutes per problem. The tougher ones might take 2 to 3 minutes.
We use a different variable for K.
Very good. I was going to say that. I was going to wait for somebody to say it. K in this problem is defined as the spring stiffness, isn't it? So instead of using K, use A or something else for the direct variation constant. Okay? You know, we've been writing like y equals kx. Write y equals ax instead. Because you're going to probably use K for something else in this problem. General formula, P equals what? P equals what? P for period, by the way, of oscillations. James? The general formula, I'm saying. Sorry, what would the formula be?
I wrote P equals J M squared over K squared.
Careful. You're very close. What did James have to do instead of m squared and k squared? Morgan? Yeah, root m over root k. Be careful, James. It says square root, okay? All right, very good. So James chose J for his own name, for the constant. That's fine. Use whatever letter you want. Doesn't have to be K. I wouldn't use K because we use K already in this problem to define a different variable. We're given all this information. Period is 9.2. Mass is 150. Stiffness of the spring is 70. Plug those numbers all into this, please. By the way, keep in mind that you could put m over k all under one radical too. Okay, another alternate way to write this. I'll write it on the right. Another way to write this would be like this as well. Okay? Because root m over root k is really just root m over k. It's one of our laws we went over earlier in the year when we did radicals. It doesn't matter, it's the same answer, obviously. What does j become? Or what does the constant become? Whatever you have for a letter. What does the constant turn out to be? To the nearest? To the nearest 2 decimals. Nearest hundredth, sorry. Nearest hundredth. James, go ahead.
6.29.
Is it 2.9? Is that what it turns out to be when you round?
It's 2.85, so I just rounded it.
Yep. All right, that works. I wrote 6.28. I don't know. I might have just rounded earlier myself. Or you know what I might have done? Did you take the square root of this? Get a number, take the square root of this?
I got 6.285, so I just rounded it to 2.8.
No, I'm not saying that, but depending on where you rounded, like if you round this answer, then divide those two numbers, or if you just take the square root of the quotient like this, you could get 2 different answers on your rounding. So the reason I was pointing out 6.28, what is 6.28? Anyone know? Does that number ring a bell? Pi times 2, very good. What's pi? Approximately. Yeah, what's double 3.14? 6.28, approximately. Now, James, yours is actually probably better because it is 2 pi, the ratio. And pi is 3.1415 or something like that. So if you doubled it, it might come out. But the idea is what I'm trying to get is that actually with simple harmonic motion, this is what this is called, with oscillating motion in physics, the constant in the front is 2 pi. It's actually the value 2 pi, which in this case we'll write 6.29 is fine. But when we write the formula in physics, we write this. This is one of our formulas in physics. P equals 2 pi root m over k. Well, 2 pi is what James just said. This is really just that constant that we solved for, 6.29. Okay, and then the second part of this problem is to do what? It's to solve for something else given more information. So this problem says, what mass would produce oscillations of 15 seconds? What does that mean? Oscillations of 15 seconds. Where's 15 going to go? Where's it going to go, Will? Why, Will?
Because that's the amount of time.
Good. Period is a measurement of time. The units of 15 are 15 seconds, so 15 has to go in for period. Very good. And it said what mass, right? What mass would produce this? So we're solving for m, it looks like? Yes, we're solving for m. And it said with a spring stiffness of 40 newtons per meter. Now, see how I wrote this all as one radical? This is where it actually might be useful to break this radical up back to what we had. Because we're going to have to solve for m. So it might be useful in this case to do this. Write the radicals separately. Even though, again, writing the radical like this is the same thing as like this up here. These are identical, really, but I'd probably choose this method because it already separates these two, and I'm trying to find m. Does that make sense? Isn't it logical? I'm trying to show you guys like smart approaches, or not smart, optimal approaches to problems. You could write it like this, plug in a 40 here, and then some students get confused because the radical is around both. How do you get rid of this? Well, if you write it separately like this, it's very obvious now. Just multiply by root 40 over here to get rid of the root 40. But if it were in here, it might be a little bit confusing. You might have trouble understanding how to isolate it. So let's move the root 40 over and move 6.29. How do I get m? How do I get m? Square both sides. Okay, m will turn out to be 228 kilograms. Homework for this, make sure to do it. Private quiz should be real easy. But I'll tell you now that you're going to have a problem that's not a word problem for sure, but then you're also going to have a word problem of sorts. Something like this, if you can do this kind of problem, you should be fine. Okay? Anybody that wants to see me for help on stuff, I know I wasn't here.